So in the binary case, remember, we generally had this. We had a mean S0 up here, and a mean S1 down here. And as long as each of these symbols had the same probability, what we did is we went right in the middle. And we had exactly one threshold, and that's all. Now what do we have? We have this. Let's say m is equal to 4. So if, it's worth pointing out that if h is greater than 0, as it should be, because if it's not, then I probably designed my filter stupidly. If h is greater than 0, and under my assumption that alpha 0 is greater than alpha 1, greater than alpha 2, and so on, then if I multiply all these by positive h, it makes no difference. And each of these is equal to si. So that's S0, S1, S2, and so on. So in other words, I'll have S0 here in 4-ary, S1, let's say here, S2, let's say here, and S3, let's say here. So if I'm, let's say I send a 1, and I want to know what's the probability of error given that I sent a 1. Where should I set my threshold, do you think? It's not clear, right? Because I got a signal on this side, and a signal on this side. So it's kind of a trick question. In fact, what you need are 2 thresholds. So in other words, a threshold to distinguish S1 from S2 and S3, and another threshold to distinguish S1 from S0. So in other words, in this range, you would be picking 1. Similarly, S2, in this range, you'd be picking 2. S0 and S3, because they've got the only signals that you can confuse them with are on one side, it's okay to do it one-sided. So over here, everything greater than this value, you'd be picking 0. And everything less than that value, you'd be picking 3. So, what we're going to do is we're just going to, if I have time to show this, we will, but otherwise you can take my word for it. What we're going to do is we're going to go with the nearest neighbor principle. Thus, if I have a received value, y, what we're going to do is we're going to pick Si that is closest to y. And what that is going to do is it's going to mean that some values have 2 thresholds. So this gets even more fun in 2 dimensions. So if I can, so this is just a 1-dimensional signal space where my signals can be represented with 1 coordinate. So now I have thresholds, possibly 2 thresholds like this. In 2 dimensions, it gets kind of fun. If I have a signal space that looks like this, now my thresholds are regions. So for instance, anything in this region, I would map to, let's say that's S0, I'd map that to 0. But we'll talk about that when we start talking about 2-dimensional constellations. Okay, anyway, some values have 2 thresholds. So remember, I'm arranging these by S0, S1, S2, S3. So the thresholds, because I'm going by the nearest neighbor principle, the thresholds are always exactly halfway between these points. And furthermore, because I assumed that S0 is an S1 greater than S2 and so on, for S0, or excuse me, for 0, beside 0, let's say y is the received value. Beside 0, if y is what? Well, what's the set of points on the number line that's closest to S0? Well, it's obviously everything to the right of S0 is closest to S0 than any other point. To the left of S0, we're still closest to S0 as long as we are more than halfway from S1. So the one threshold here would be halfway between S0 and S1. So y is greater than S0 plus S1 over 2.
That's only true if the probability is all equal. Right?
Correct. So that, otherwise the nearest neighbor principle doesn't work. That's worth pointing out. Only optimal if all symbols are equiprobable. Okay, for 1, I will decide 1 if, let's assume that there's more than 1 point. In other words, m is greater than 1. So the set of points that's closest to S1 is less than this. So S0 plus S1 over 2 is greater than y. And between S1 and S2, I have basically everything to the right of halfway between these 2 points. That's S1 plus S2 over 2. For 2, so on, for any I, where I is less than m, decide I if Si minus 1 plus Si over 2 is greater than y, is greater than Si plus Si plus 1 over 2. And finally, the last one. So the only two that are one-sided, the last one would be Sm minus 1. I is less than, that should be I is less than m minus 1. So the only other one that's one-sided is Sm minus 1. Sm minus 2 would be here. So everything to the left of halfway between Sm minus 1 and Sm minus 2, I would decide m minus 1. That is if y is less than Sm minus 2 plus Sm minus 1. And there you have it. There are your decision regions. The set of points in a geometric space, that's, if you have a collection of points in a geometric space, the set of points that is closest to one particular point is called the Voronoi region. And there's tons of mathematical literature on that. And basically what I've done for you here is I've broken down the Voronoi region for m consecutive points on a one-dimensional line.